Okay. This problem gets thrown in here just as a review, just to keep our minds right and our minds sharp, because it doesn't quite fall in line with the stuff we've been doing, dealing with magnitude and direction angle and writing that new format for the vector. But this is just keeping us fresh on linear combination. Remember, linear combination is just a different representation of the run and the rise of a vector. So vector v has this linear combination. That is essentially the exact same thing as saying vector v has these components. Okay? And keep in mind, those components are the run and the rise. Right? So if we start at the origin as our initial point, and we run 6 units, that's 6 positive units, and we rise -6, that would mean we're falling 6 units down to here. Our vector goes from here to there, right? Now from that, they want to know the magnitude and the direction. Let's do this. How about we do this? I mean, the formula still works. I don't want to shy away from the formula. The magnitude of a vector is still the square root of v1 squared plus v2 squared, right? We always have this formula to help us find the magnitude. But let's be problem solvers about this for a second. I'm going to throw something at you here. Okay, I'm going to put something up here that you might not remember, maybe you do, who knows, but it's something different to keep things fresh. So magnitude, keep in mind, is the actual length of this vector right here. The arrow is not saying it goes forever and ever and ever. The arrow is saying it stops here. This is the length. All right? So this distance was our run for this slanted line, this vector right here. That's 6. This distance was our rise, right? We said that was -6. Now, distance shouldn't be negative. I've been labeling these as negatives here because I want to emphasize that point when we're doing the calculation of theta. But bear with me for a second. Let's think back to geometry, if you will. Here I have drawn, with this vector and its 2 components, I have drawn a right triangle. This right triangle has 2 legs that have the same length. Ignore the fact that this is -6. The absolute value of that distance is 6. This is 6, right? We have a special name for a right triangle that has 2 legs that are the same length. It is called an isosceles right triangle. Okay? And in an isosceles right triangle, you also have congruent, what we call base angles, right? So the angles that are opposite these congruent sides are also congruent. I know I'm throwing out geometry words in a pre-calc room, but so be it. Now with this piece of information, this distance and these angles, we can find them without doing any calculations whatsoever, if you remember what we call our special right triangles from geometry. So if this is 90 degrees, and all 3 angles of the triangle have to add up to 180, and that's 90, that means these 2 angles have to add up to 90 degrees, because 90 plus 90 is 180. And if these 2 angles add up to 90 degrees, each one of them has to be 45. So wouldn't you know, we just found something extremely valuable for the direction angle of this vector. If we know that this piece is 45 degrees, then the direction angle, which goes from here all the way over to here, is 45 degrees short of that full 360. I'm going to say that again. Direction angle always has to be measured from your positive x-axis, and we swing in this direction. This is counterclockwise, right? Standard position. So the vector that goes down here starts here, swings all the way through all of this, and stops in that space. If this piece right here, this part is 45 degrees, that means this entire angle is 45 degrees short of finishing that full rotation, right? So the direction angle here, theta, is 360 minus 45, which is 315. you could also, and we did this when we were talking about standard position the first time with unit circle, you could also call this negative 45 degrees if you want to talk about it being measured down, right? When we measure clockwise, that's negatively measured angles. So 315 degrees, negative 45 degrees, interchangeable values, right? Now let's get back to finding the magnitude. So we have the direction angle. We said this is 45 degrees, so this is also 45 degrees. One of the more, I would like to think it's common, I haven't taught geometry in 15 years, but one of the more common or maybe obscure facts that you cover, and one of the topics that you cover in geometry is what we call special right triangles. One of those right triangles is called a 45, 45, 90. And the side lengths of a 45, 45, 90 have a pattern to them, right? We already said if it's 45, 45, it's isosceles. These two side lengths have to be the same. The hypotenuse of a 45, 45, 90 triangle will always be whatever, well, let's call these x, yeah? Whatever the lengths of the legs are times radical 2 every single time, okay? So if I have this triangle, which I see 45, 45, 90, these two side lengths are 6, then I know that this hypotenuse is 6 radical 2. And that also happens to be the magnitude of this vector, okay? So just for fun, it doesn't ask me to do this, but I'm going to do it because it follows a theme of some of the previous videos leading up to this. Now that I know the magnitude and the direction angle, I can express vector v like this. 6 radical 2, right? We put the magnitude first, and then inside these brackets we put the cosine and the sine of the direction angle. Okay, so this format and this format look very different, but they express the same vector. This one in terms of its run and its rise. This one in terms of its magnitude and its direction angle.